Alright, so for the past 40 minutes just now, we already look into the introduction as well as the performance parameters of jet engine, including thrust force as well as the factors affecting thrust. So let us move into the another subtopic under performance parameters of jet engine, which is engine performance. Under the engine performance subtopic, we will go through some few elements of the factors that affecting the engine performance. How do you measure the engine performance? How do you say that this type of engine performance is better than the other? The performance of an aircraft engine may be criticized by its ability to provide the necessary thrust force needed in propelling an aircraft efficiently in its different flight regime. So in order for us to say that an aircraft engine is having a better performance than the other, is basically based on whether the engine can provide the necessary thrust force. Engine performance are identified as follows. So we will look into the propulsive efficiency, and then we will then continue on looking into the thermal efficiency, followed by propeller efficiency, okay, and then overall efficiency for aircraft engine, the takeoff thrust, specific fuel consumption, and finally the aircraft range. So those are the normal performance parameters when we talk about engine performance. Before we go into any further, right, we need to highlight a few things here where we all know that the military aircrafts are powered by engine that fulfill its mission requirement. For this reason, the takeoff thrust, the ability for maneuverability, and affordability are the critical issues with some sacrifice of its fuel consumption in some types like fighters and interceptors. So when designers, military aircraft designers decided what are the engine, the propulsive system that they require, they, apart from looking into the takeoff thrust, the ability to maneuver, and of course affordability, right? So there are some sacrifices that need to be done. Maybe the engine is high performance but having a bit more fuel consumption, or it can also be used for things like fighters. It has to be, it should be moving very fast, all right, without being detected, and it needs some sacrifice. It needs some balance between what is needed from the mission profile, or what need to be produced. Like maybe if you want a better performance, you need to have more cost to it, right? For both the civil and military transport, normally the specific fuel consumption as well as the aircraft range are the two critical design issue, right? You do not want to have high performance aircraft or high performance engine having used a high specific consumption. So you need to burn more fuel. You need to in order for you to achieve the mission, or at the same time, aircraft also need a better range. For long haul aircraft, you need to provide a propulsive system that can travel as far as possible with the minimum fuel being consumed. So in both types, several efficiencies related to the conversion of heat generated by fuel burning into thrust are important. Let us look into the first one, propulsive efficiency, right? So what is actually propulsive efficiency? It is actually the efficiency of the conversion of kinetic energy of air when passes through the engine into a propulsive power. So you want to convert kinetic energy of air into propulsive power, and that is what we call the propulsive efficiency. So it is identified by aero engine manufacturers as an external efficiency. Okay, so it is influenced by the amount of energy wasted in the propelling nozzle and normally be denoted by zeta P. Okay, the thrust efficiency can be defined as follows. It is a ratio of the thrust power to the power imparted to the engine airflow. Right? So this is equation 3.8a, or simply the thrust power sorry, to the thrust power plus over power wasted in the exhaust. Or it can be either equation 38a or 38b, which will be denoted here as the first expression of the propulsive efficiency, the simplified form of the propulsive efficiency. Another definition being used in the literature, okay, or in the manufacturing of aero engine, is the thrust power to the ratio of the rate of kinetic energy added to the engine airflow, 3.9, and that what being defined in our earlier explanation. So this will be referred to as second expression. So the first expression and the second expression being denoted by equation 3.9. The first expression 3.8a or b, and the second expression is being denoted by 3.9. However, for scramjet, for ramjet, or in the turbojet engine families, the first expression has the form as follows. So we have equation 3.10a and 3.10b. The zeta p can be expressed as follows. So you can have this is quite simplified, right? So where you have only the portion of the best flow, the temperature, the velocity, as well as the exit velocity. However, for 310b, okay, you have the component of the airflow ratio, fuel air ratio, F. You have the component of the pressure, as well as the component over this expression. And this is normally being used by the aero engine manufacturers when they want to decide what is the propulsive efficiency that can be produced by their engine. The second expression, okay, so is being denoted by 311a and b, where the two expressions are actually identical. If the nozzle is unchoked, okay, if the nozzle is unchoked, where PE minus PA or PE is equal to PA, exit pressure is equal to the ambient pressure, and the component of the F, air fuel to air ratio F, is negligible. So 310A and B will be identical to 311A and 11B. So the following third expression can be obtained, right? If the nozzle is unchoked, we can have a more simplified expression, which is equation 312. And this is normally being used in as a simplified version of the for turbojet engine, ramjet, and scramjet engine. The zeta P, the propulsive efficiency, is just the component of the velocity, velocity of the aircraft, as well as the exit velocity. All right. So, however, for different type of engine like bypass engine for turbofan or propeller fan, the air coming into the engine is split into two streams. One is the airflow that goes through the fan of prop fan, and is known as the cold stream, normally being denoted as the subscript C, okay, while the other passes through the engine core, which is including the compressor, the combustion chamber, and other subsequent module, and is known as the hot stream. And normally we denoted it as subscript H. Applying the same principle and employing the first expression, we get the following. So instead of having one type of temperature, now we have hot temperature and cold temperature, right? This is what we can express for turbofan or turboprop prop fan type of engine, 313A, where TH and TC are the thrust force generated by the hot and cold stream respectively, while WH and WC are the wake losses of the hot and cold stream respectively. This relation can also be written as this expression, right? And this 313B, this is the first expression for the propulsive efficiency in turbofan engine. Okay, the second expression shown in equation 311A can also be written using the two hot cold streams. We can rewrite it as 314A. So when the two nozzles of the hot and cold stream are unchoked and the fuel air ratio is negligible, both expressions yield the following. And we have 314B, where beta in this equation is actually the bypass ratio, right? Bypass ratio between the mass flow rate of the cold as well as the hot air. So mass flow rate of the cold over mass flow rate of hot air is having a symbol beta, right? Some engine having mass only 80% of the air will go to the bypass, the cold air, the cold flow, and the hot flow only 20%, and some having even different ratios. The propulsive efficiency for turboprop engine, so next we move into turboprop engine propulsive efficiency, can be written as this expression 315. Okay, the propulsive efficiency for a turboprop, a turbojet, and turbofan engine can be illustrated in figure 312 and 313. Figure 312, whereby 313 illustrate the propulsive efficiency for single and contra-rotating prop fan engine. Okay, so this figure 312, it is a combination of turboprop, turbojet, and turbofan engine. And this is reproduced from Rolls-Royce book 2007. So imagine this is the pure turbojet. Okay, just having the core of the engine. Okay, so this is the propulsive efficiency zeta P. This is against the x-axis, the airspeed. If you look at the pure turbojet engine, okay, it is basically as the airspeed increases, the propulsive efficiency increases in percent, right? However, for the turbojet having low bypass ratio meaning that we have a low cold stream of air, okay, a low mass flow rate for the stream of air. So this is the line, and the second line, and then we have the high bypass ratio for turbojet. Okay, so the efficiency is getting better, right? Compared to the low bypass of a turbojet, as well as compared to the pure turbojet, right? However, if we look here for turboprop type of aircraft, okay, turboprop type of aircraft. So it is having a far better efficiency at a low speed. Even for example, like we take 200 mile per hour. Okay, for a turbojet engine, it is around 25% efficiency, propulsive efficiency. For low bypass turbojet engine, known by the name of turbofan engine, low bypass. So it's already 40%. Going into high bypass turbojet engine is already 48%. But for a turboprop engine, it can reach up to 65% propulsive efficiency, right? So you can see the advantages of having turboprop, which is more superior at the low speed compared to a turbojet engine. Looking into the other type of engine, we have contra rotating fan. I believe you still remember different type of engine. This is a contra rotating. There are two set of propeller fan. One is moving the opposite direction of the other the other set of fan. Contra rotating fan compared to a propeller fan. So both are being used at a low speed aircraft. So you can see here at 200 mile per hour, a contra rotating fan propulsive efficiency reaches 50%, but the propeller fan already reaches 65% at 200 mile per hour. Okay, right. In this presentation, I purposely did not provide any examples because there are actually many examples can be shown for each one of it, and probably Dr. An can later on provide examples when you go through the tutorials for each one of these performance parameters. Okay, so let us move into the thermal efficiency. Right, just now is propulsive efficiency, zeta P. Now we move into zeta TH. Okay, so what is actually thermal efficiency? It is the efficiency of energy conversion. Propulsive efficiency is the conversion of the kinetic energy, but thermal efficiency is the how much efficient the engine can convert the energy within the power plant itself, right? So it is considered as internal efficiency, whereas the propulsive efficiency considered as the external efficiency. And while the thermal efficiency is denoted by zeta TH, and two forms for such efficiency are defined for the following two groups of engine. Okay, the first one, ramjet, scramjet, turbojet, and turbofan engine. The thermal efficiency is expressed in equation 317. It is actually the ratio of the power imparted to the engine airflow, W dot out, over the rate of energy supplied to the fuel, in the fuel, Q dot in. So it is easy to note that the denominator, okay, of equation 38A that we have seen earlier is equal to the numerator. We can see that it is this is numerator, denominator of equation 3.8a. You may want to refer back equation 3.8a. That is actually the top portion here. Okay. For specific ramjet and turbojet engine, using the first expressions for the propulsive efficiency, the following first expression, zeta TH, is obtained. Okay, this is thermal efficiency for ramjet and turbojet engine is expressed here, where QR over here is the heat reaction of the fuel use. Other names for QR normally be used as the lower heating value, LHV, or it normally being used as QHV. In our case, we are using the heating value for heating value and normally being used in any problems in the propulsion course. Assuming unchoked nozzle, right? So we do not have the components of the pressure time the area. The W dot out is equal to this expression, and from the second expression for the propulsive efficiency, the following second expression for thermal efficiency can be obtained in equation 317A and 317B. Right? So for unchoked nozzle and negligible fuel air ratio, the following third expression can be given. So you can have this expression, and sometimes it's being used QR, sometimes most of the time we'll be using QHV. For two stream of engine, turbofan and prop fan, you have the other component. You have the hot and the cold component of mass flow. Similarly, assuming unchoked nozzle and negligible fuel to air ratio, we get expression 320, which actually you can compare it to 318 directly. For turboprop and turboshaft engine, the output of turboprop or a turboshaft engine is largely by shaft power. In this case, the thermal efficiency is defined as the P total over the M dot FQR, where P total is the total power produced by the turboprop or turboshaft engine. For a turboprop engine, P total equal to the propeller power plus propeller jet, which is equal to this expression, where SP is actually the shaft power, T is the thrust, and Vj is the jet velocity. Okay, can be expressed in this relation. And for turboshaft engine, say driving the rotor of helicopter, the total power equals to the rotor power. Okay, rotor power is being expressed as this component. Okay, again, example is not being shown because it limited time that we have, so we can have it in the tutorial session. For propeller efficiency, let us move quickly. Propellers are used in both piston and turboprop. Shaft power is converted to the thrust power, and the propeller efficiency is defined as the ratio between the thrust power generated by the propeller and thrust power generated by the propeller, TP, which is more, this is equal to UTPR, right? The velocity time the thrust power generated by the propeller to the shaft power SP. So this is the expression for turboprop or piston engine. When an applicable amount of thrust is obtained from the exhaust gases TE, right? Thrust from the exhaust TE in a turboprop engine, we have another component, another element being introduced. Equivalent thrust power, ETP, right, is expressed in terms of the shaft power, the propeller efficiency, as well as the exhaust thrust power. Okay, so this is the expression 323A. And alternatively, an equivalent shaft power, ESP, is used instead of the equivalent thrust power. You have equivalent shaft power, or the other one is equivalent thrust power. They are related to each other. ESP equivalent to ETP over zeta PR, propulsive propeller efficiency. Okay, and the exhaust thrust is expressed as the following. Okay, the total thrust force is given by the relation. You have the total thrust force equal to the propeller thrust plus the exit thrust produced, and the propeller efficiency can be expressed as equation 3.25. You have the equivalent shaft power over here in the denominator. Let us look go into the next one, which is the overall efficiency, the product of propulsive and thermal. Just now we already gone through propulsive efficiency. Then we look into the thermal efficiency, basically the product of both propulsive and thermal efficiencies are it is appropriate to be called as overall efficiency. So that's how you determine. And the overall efficiency is not just the propulsive efficiency, it is a combination of the two, and the product of propulsive and the thermal efficiencies. So since the overall efficiency depends on the velocity and the thrust T, which balances the aircraft drag, overall efficiency is actually not a parameter of the engine alone, but characterizes the engine or aircraft combination and its state of operation. So for turbojet with unchoked nozzle and negligible fuel to air ratio, the overall efficiency zeta O equal to the thermal efficiency times the 2U, 2 times the aircraft speed divided by the aircraft speed plus the exit velocity. Okay? Right. Let us look into the takeoff thrust. An important parameter that defines the ability of an aero engine to provide a static and low speed thrust, which enables the aircraft to take off under its own power without any propelling mechanism to propel it, right? Equation 3.3, the static thrust of a turbojet engine with an unchoked nozzle is expressed by this relation. Takeoff thrust equal to mass flow rate of the air times 1 plus air fuel to air ratio times the velocity and exit. Okay, so this is how you calculate the takeoff thrust. From equation 370, A, when U equal to 0, because during takeoff, the airspeed is 0. You only have the exhaust velocity, exhaust speed. Okay, so it can be expressed here. Okay, from equation A and B, then the static or takeoff thrust is given by the relationship. So you know the thermal efficiency as static. This is the expression. So you combine A and B, you can then get the takeoff thrust for the aircraft in terms of 3.27 B. Right? For a constant value flow rate and thermal efficiency, then the takeoff thrust is proportionate to the 1 over UE, the exit velocity. And the above relations outline one of the advantages of turboprop engine, okay, over turbojet as well as turbofan engine. Turboprop engine accelerate a large mass flow rate of air to a small exhaust velocity, which is in turn increases the takeoff thrust. Okay, you want a higher takeoff thrust with a small amount of exhaust velocity. Consequently, aircraft powered by turboprop engine can take off from a very short runway. That's the reason for small airports, small short runway, for city hopping type of aircraft, they normally use the turboprop engine instead of a turbojet or turbofan engine. Okay, let us move into the next one, specific fuel consumption, SFC. Okay, so this performance parameter of the engine has a direct influence on the cost of aircraft trip as well as flight economics, right? So you want to make sure the specific consumption to be as low as possible, right, for your aircraft, right? And fuel consumption is either defined per unit thrust for ramjet, turbojet and turbofan engine, or per horsepower. For turboprop and piston prop engine, propeller engine, the industry normally use per horsepower fuel consumption. Let us first look into the family of ramjet, turbojet, and turbofan engine. The thrust-specific fuel consumption, TSFC, equal to the mass flow rate of the fuel over the thrust force, which is expressed in equation 3.1 earlier, and for ramjet or turbojet engine. For equation 3.4, it is for turbofan engine. The values of thrust-specific fuel consumption, TSFC, strongly depend on the flight speed. And so its typical value for both turbojet and turbofan are defined for static condition. Okay. However, for ramjet reference value, the thrust-specific consumption are defined at flight Mach number of 2. Okay. The typical value above mentioned 3 engine type are given in this table. For example, like for turbojet, where we have Mach equal to 0, right? Turbojet and turbofan, it is at static. Okay. Thrust specific fuel consumption is between 0.075 to 0.11 kilogram for Newton hour. Okay, or for turbofan 0.03 to 0.05, okay, compared to ramjet at Mach 2, 0.17 to 0.26. You can see that the turbojet having less thrust specific fuel consumption, okay, at static compared to turbofan, right? It requires more fuel compared to turbojet at static condition, whereas of course ramjet having a higher thrust specific fuel consumption because it will consume a lot of fuel at a higher speed. Some empirical formula are available for thrust specific fuel consumption, and it is being used in this form where we have A and B component, right? For A and B, there are constants that vary from one engine to another. M0 is the flight Mach number, and theta is the dimensionless ratio. The thrust at the ratio, the ratio of the ambient temperature and ratio to the ratio of the temperature at the flight altitude, T reference. Okay. For example, like temperature at the flight altitude and a standard temperature at sea level at 288.2 Kelvin, right? Depending on the where you fly. T altitude over T reference. T reference normally at the sea level. For high bypass ratio turbofan, the values of this constant are A is 0.4 and B 0.45. Okay. Let us move into the turboprop engine. For engines which produce shaft power, fuel consumption is identified by the BSFC, the brake specific fuel consumption, or simply specific fuel consumption as defined here in equation 3.29. Okay. So when applicable, thrust is produced by the hot gases. The fuel consumption is identified by the equivalent brake specific fuel consumption, ESFC or EBSFC. All right. For turboprop engine, typical value for ESFC is around 0.27 to 0.36 kilogram per kilowatt hour, and the values of the corresponding constant in the empirical relation. And where does this number coming from? Basically, people doing research, they provide a table or on empirical relationship, and that's how they got this A and B, 0.2 and 0.9 respectively. Right, the final part of our presentation will look into the aircraft range. Okay, with regard to aircraft range, The aircraft range is a design parameter of the aircraft and based on which number, location, and capacity of fuel tank in the aircraft is determined, right? So whether it is under the undercarriage the very of the aircraft, right, or the fuel tank is located at the wing box. They provide a wing box, or they provide it at the rear of the fuselage. Okay, so and how many fuel tank, what are the capacity, where is it located, also very important to determine the aircraft range. The aircraft weight is composed of the structural weight and the payload, including the crew members, food and service supplies, as well as the fuel weight. And during any trip, only the fuel weight is changeable, because when you at a takeoff, probably you want to have maximum. You have a limitation of maximum takeoff weight, right? So you can when you already travel half of the distance, probably you have already used up half of the fuel. That's where the fuel weight not going to be constant. It's going to be reduced. Now consider the cruise phase in a flight trip where the aircraft flies at a constant speed. Ignoring the climb and descent phases, it may assume that the cruise distance is equal to the trip distance of the aircraft. During cruise, the aircraft is subjected to two vertical forces, only the lift and the weight, which are equal in magnitude, and the two horizontal forces, the thrust as well as the drag, and which are also equal in magnitude, like being shown schematically in this particular diagram. So the lift is equal and opposite direction to the weight. The thrust is equal and opposite direction to the drag. Then what we can say is that T, the thrust equal to the drag, mg times the d over L, where m is the instantaneous aircraft mass and g, of course, the gravitational acceleration. Thus, we can rearrange this equation to this expression. So since the rate of fuel consumption is equal to the rate decrease of the mass of the aircraft, then we can write the mass flow of the fuel equal to this expression, whereas in this particular expression is the distance along the flight path. Rearranging, you will get the final expression for change in the distance. Integration of the above equation, you will get the range of the aircraft S, right? Okay, in terms of the component here, 3.31, where M1 and M2 is basically the mass of the aircraft initial and final. Okay, initial and finals from starting point, from point A to point B. Okay, point B is the final mass of the aircraft. So equation 3.25a, from there, the above equation is reformulated. So you can reformulate it for 3.31 to 3.32, and it is known as the popular Breguet equation. Okay, normally you use this expression or Breguet equation when you conduct your aircraft design exercise to determine the range of your aircraft. So another expression for this range is obtained from the overall efficiency, right? Equation 326 as well as 331. Okay, you can have the overall efficiency component over there, and that can also determine the range of the aircraft that you design. In above equation 332 and 333, the ratio between the lift and drag forces may be alternatively written as the coefficient of lift and coefficient of drag, and where lift force coefficient is calculated as usual from the relationship where W is the aircraft weight and SW is the aircraft wing area. The drag coefficient is calculated from this relationship where K1, K2, and CD0 are typical function of the flight Mach number as well as wing configuration. So depends on whether you have different flight Mach number, whether you have flat position and other wing configuration, it will be having a different values. The CD0 term is the zero lift drag coefficient, okay, which accounts for both frictional and pressure drag in the subsonic flight and wave drag in the supersonic flight. K1, K2 terms account for the drag due to lift, and normally K2 is very small and approximately equal to 0 in most fighter type of aircraft. So what can we conclude here is that it is clear that from both equation 332 and 331 that to maximize the range of an aircraft flying at a specified speed, first you have to fly at maximum lift to drag ratio. Okay. The second one is that to have the highest possible overall efficiency, zeta 0, zeta O, and then the third one to have the lowest specific fuel consumption, and finally to have the highest possible ratio between the aircraft weight at the start and the end of cruise, okay, M1 and M2, right? For a propeller or reciprocating turboprop engine, a similar analysis may be followed. You can go through it, but this is the simplified version for to find the range. Okay, substituting in equation 331, you can get a range for the turboprop aircraft as 3.334. Similarly, to maximize the range, the lift to drag ratio, the propeller efficiency, and the ratio between the aircraft weight at the start, M1 and M2, right, have to be chosen as maximum, while the fuel consumption, ESFC, equivalent specific fuel consumption, have to be minimum, so that S can be increases. Airlines and aircraft manufacturers, they are normally following form for Breguet in relation for turbojet or turbofan engine. You can use equation 335, and then for turboprop engine you can use expression 336. Well, in this particular case, C is the specific fuel consumption expressed in pound fuel per pound thrust per hour, right? Or in term of pound fuel over equivalent shaft horsepower per hour. So with that, we will adjourn our session for today to continue on the subtopic of turbojet in our class next Monday, and to look over the thermodynamic cycle of a single spool, performance parameters, important definitions, double spool, thermodynamic cycle of a double spool performance parameters, and finally micro turbojets, before we move into the third lecture number 11 for turbofan type of engine. So thank you for your attention.